Welcome to the Deep Dive. Today we're embarking on a journey into the very bedrock, of our digital world.
Right, something that's pretty much everywhere but often unseen.
Exactly. A ubiquitous force operating silently behind the scenes. I mean, think for a moment about, that smartphone in your hand, or the colossal server farms powering giants like Amazon, Facebook, Google.
Critical infrastructure, too.
Yeah, critical infrastructure around the globe. What's humming beneath it all, making it work seamlessly, reliably, often for years without a single reboot.
More often than not, it's Linux.
It is Linux. And it's not just an operating system, is it? It's really a digital workhorse.
It genuinely is. And that stability, well, it isn't just a convenience. It's actually a profound operational and economic advantage.
How so?
Well, imagine the cost. The astronomical cost of downtime for, say, a global e-commerce platform. Every minute lost translates to millions in revenue. Linux's kind of set it and forget it reliability fundamentally redefines disaster recovery strategies. And it drastically reduces operational overhead. It lets administrators focus on innovation, not constant firefighting.
Oh, okay.
That's the real insight into its enduring value, I think.
That profound stability, yeah, it really underscores its importance. And that's precisely why we're taking this deep dive today. We're looking into the foundational concepts of Linux system administration.
Mm-hmm.
Our mission for you, our listener, is to meticulously extract the most vital nuggets of knowledge from a curated stack of sources. We've got academic notes, syllabus excerpts, expert talks.
All sorts of things.
All sorts, yeah. To ensure you gain a quick yet remarkably thorough understanding of Linux's core principles.
And the goal here is really to give you a powerful shortcut.
Mm-hmm.
We want to equip you with a solid grasp of the essential architecture, the key commands, the fundamental principles, everything that empowers system administrators to manage and secure these powerful systems.
Right.
Expect some surprising facts, hopefully some practical takeaways, and maybe those aha moments that clarify complex ideas, but, without overwhelming you with just tons of information.
Okay, so what does this deep dive look like today? Well, we'll begin by establishing the fundamental role of system administrators. Then we'll delve into the unique features and the underlying architecture of Linux itself.
Nuts and bolts.
Exactly, the nuts and bolts. From there, we'll get practical with essential commands for day-to-day operations. Then we'll move into the critical areas of managing processes, users, networking, and foundational security concepts. It's going to be an insightful journey, I think.
Sounds good. Let's dive in.
Okay, so we've glimpsed Linux's pervasive reach. Now it's time to dig down, right? We're going to uncover the very bedrock of this digital world, starting with those foundational concepts that underpin everything.
Foundations first. Makes sense.
Let's begin by defining who these architects of the digital realm truly are. System administrators. What exactly is system administration at its core?
Well, at its core, system administration is basically the comprehensive management and maintenance of computer systems. But I think to truly grasp its significance, you need to consider that system administrators hold a pivotal role, and they possess immense power within an organization.
Okay.
They are, in essence, the super users of the computing infrastructure. They're entrusted with its health, its security, pretty much everything.
Super users. That phrase really does highlight the responsibility, doesn't it? So beyond just, keeping things running, what are the multifaceted responsibilities that fall under their purview?
Oh, their tasks are indeed multifaceted. And they go far beyond merely fixing things when they break, System administrators are responsible for securely accessing restricted files, installing and configuring critical software, optimizing system performance.
Performance is key.
Absolutely. And they possess broad administrative privileges to oversee the entire digital environment. This means proactive design, continuous maintenance, vigilant security, and ensuring business continuity. They're the ones who build and maintain the digital backbone that, every modern organization relies upon.
And this brings us to a crucial question then. With so many operating systems available, why is Linux so frequently the OS of choice for these highly critical, backbone roles, especially in server environments?
That's where the Linux advantage truly shines. And it comes down primarily to its unparalleled stability and reliability.
That stability again.
Exactly. Linux servers are renowned for their ability to operate nonstop for extended periods. I mean, we're talking sometimes for years without requiring reboots.
Years, wow.
Yeah, which is absolutely paramount in professional server environments where continuous uptime isn't just desired, it's a fundamental business requirement. Unlike, other operating systems that might need frequent patches and restarts, Linux's robust design and efficient kernel management allow for incredible resilience.
Okay.
This means fewer interruptions, predictable performance, and dramatically lower operational costs over time. Just makes it incredibly valuable for critical server operations.
That deep reliability makes perfect sense. It's about minimizing headaches,
Yeah.
maximizing efficiency. Okay, now let's unpack Linux itself.
Mm.
Where did this powerful, dependable operating system even come from? And what's its underlying philosophy?
Well, the genesis of Linux is quite a compelling story, actually. It's rooted in a philosophy of openness. We credit Linus Torvalds, right?
Yeah.
Then a computer science student in Finland back in the early 90s.
Just a student, yeah.
Just a student. For his revolutionary idea, he developed the Linux kernel, which is the absolute core of the OS, the part that directly talks to the hardware from scratch.
Mm-hmm.
He was inspired by Unix, sure, but his vision was fundamentally different. He wanted it to be openly receptive to user changes, to modifications. Yes. This commitment to an open model fostered this vibrant global development community that continues to define, scrutinize, and rapidly evolve Linux even today. This collaborative, transparent approach is truly at its heart.
That open source philosophy seems to be, a defining characteristic.
Let's
delve into some of those hallmark features that make Linux such a powerful and popular choice for sysadmins. First, this idea of being open source and, importantly, cost-free.
Absolutely. Linux is fundamentally open source. That means its entire source code is freely available for anyone to download, inspect, modify, distribute, whatever.
Huh.
The immediate benefit, obviously, is zero licensing cost for the OS itself, which is huge. But the deeper impact, I think, goes beyond just cost. It offers immense flexibility, transparency, and a level of community-driven innovation that proprietary software just can't match.
Right.
Developers, administrators, they can tailor it precisely to their needs. They know exactly what's under the hood.
And speaking of efficiency, how does Linux handle something like system updates? Is it a complex process, or is there a more streamlined approach administrators rely on?
That's a great question, and it's another area where Linux really shines. A huge time saver for administrators is the remarkable ease and efficiency of updating software or even the entire OS.
Mm-hmm.
They can perform these critical updates with a single, straightforward command. For example, on a Red Hat or CentOS system, it might be sudo yum update.
Okay.
Or on Ubuntu, it could be something like sudo apt-get update and sudo apt-get upgrade for a general system update, or say sudo apt-get install bind if you just need a specific package.
So very direct.
Very direct. It significantly streamlines maintenance processes. It often allows for rapid patching of vulnerabilities or deployment of new features across many servers simultaneously. Big time saver.
Now, for someone coming from, say, Windows or Mac, one of the most striking differences in Linux is the interface. Linux offers both a graphical user interface, the GUI, and a command line interface, the CLI. What's the fundamental distinction? And maybe more importantly, why is the command line so profoundly powerful for system administrators?
Right. Well, Linux does provide a robust GUI experience, comparable to Windows or Mac OS, but its true power and versatility, especially for administrators, reside in the command line interface often called the terminal or shell. This text-based interface offers just unparalleled control, precision, and critically scriptability.
The scripting.
Yes. The true aha moment for many admins isn't just the control the CLI offers, but its composability. You mentioned Legos earlier. It's like that.
Right.
You can take the output of one command and pipe it directly as input to another. You create custom, powerful workflows that, honestly, no graphical interface could ever provide.
Yeah, you can't really do that with clicks.
Exactly. This allows for automation and problem solving at a scale simply impossible otherwise. It's a real paradigm shift in how you interact with the system, making complex tasks almost routine.
So it's not just about clicking buttons. It's about, speaking directly to the system and even building new tools on the fly.
Yeah.
And speaking of variety, there's this whole world of distributions or flavors of Linux. What are these? And how do they differ in a way that matters to an administrator?
Yeah, distributions or distros. They're essentially different packaged versions or flavors of the Linux operating system. Think of them as different brands or configurations built around the same core Linux kernel.
Okay.
Prominent examples include Red Hat Enterprise Linux, RHEL, Ubuntu, Debian, Fedora, CentOS, lots of them. And many popular distributions, like Ubuntu, are even built upon others. Ubuntu, for instance, is based on Debian. This rich variety gives you immense flexibility. If one distro doesn't suit your needs or, your organization's requirements, there are numerous alternatives. What's particularly valuable for administrators, though, is that roughly 98% of commands and fundamental concepts remain consistent across different distributions.
Oh, that high.
Yeah, pretty much, which significantly minimizes the learning curve when moving between them. It's not starting from scratch. It's more like learning different regional dialects of the same powerful language.
That's a crucial point, minimizing relearning across different environments. Okay, and finally, a big one. Security. Linux is often praised for its superior malware protection. Is it truly antivirus-free, and what makes it so robust?
Well, it's often lauded as antivirus-free. Yeah. Not because it's totally impervious to all threats, nobody claims that, but because it is significantly less susceptible to viruses, malware, and external attacks compared to other operating systems.
Okay.
This robustness stems from several factors: its strict permission model, the principle of least privilege built into its design, and crucially, the open source nature again.
Back to open source.
Right. The global community of experts constantly scrutinizes, identifies, and rapidly patches vulnerabilities. This means Linux becomes more robust and secure with each successive upgrade. So while no system is 100% immune, its design and community support make it inherently very secure. It often negates the need for traditional antivirus software that you might find, common on other platforms.
That's fascinating. A community-driven, transparent security model.
Yeah.
Okay, so if Linux is essentially a kernel with other components, let's drill down to the very heart of it, the kernel itself and its architecture. What exactly is this kernel, and what vital role does it play?
The kernel is precisely that, the heart or core program of any operating system. Its critical function is to act as the lowest level of easily replaceable software. It provides the direct interface between the computer's hardware and its software. Think of it as the ultimate translator and resource manager. It takes your high-level user commands and applications, then translates them into low-level instructions that the physical hardware, your CPU, memory, storage devices can understand and execute. It manages everything from process scheduling to memory allocation, device input-output, the works. Without the kernel, your applications simply couldn't talk to your computer's components.
So it's the bridge between software and hardware. Okay, beyond the kernel, what are the other fundamental components that make up a complete Linux operating system? You're making it a usable environment.
Right, it's not just the kernel. A complete Linux OS comprises two other primary components: system libraries and system utilities.
Okay.
System libraries are special functions or collections of programs that let application programs and system utilities access and use kernel features. They implement a significant portion of the OS's functionalities. They're basically the reusable building blocks that software developers rely on.
Got it. Libraries and utilities.
Then you have system utilities. These are the diverse set of tools and programs designed to perform various management and operational tasks within the system. Everything from file management to network configuration. These utilities are what administrators use day to day to interact with and manage the system. Roles, CP, MV, those are system utilities.
That paints a clearer picture of how it all fits together.
Yeah.
Okay, and what about how everything is organized on the disk? Linux is famous for its hierarchical file structure. What does that mean in practical terms for navigating the system?
Yes, Linux uses a fundamental hierarchical directory structure. It's organized much like an inverted tree. At the very top is the root directory, just denoted by a single /.
The rooted.
Exactly. That's the starting point for absolutely everything on your system. All other directories, like bin for binaries, boot for boot files, dev for devices, etc. for configuration files, home for user directories, utter for user programs, and var for variable data like logs, are subdirectories that branch off from the root. This consistent, predictable, logical organization for all files and data makes it incredibly powerful and straightforward to navigate, manage, and even script interactions with the system, regardless of which distribution you're using.
It's like a very organized digital filing cabinet. Yeah. Starting from one main all-encompassing folder. That leads us directly into section 1.4, behind the scenes Linux file system fundamentals. So what's the fundamental purpose of these file systems?
Well, file systems are the organizational bedrock of Linux. They dictate precisely how and where data is stored on a disk. They ensure that data is systematically arranged, retrieved efficiently, and reliably accessible.
Okay.
Every disk partition typically has its own dedicated file system. It acts as a structured container for your information. Think of it as the blueprint for how data bits get turned into coherent files and directories.
And I understand there isn't just one type of Linux file system. What are some of the diverse types an administrator might encounter, and what are their key characteristics?
That's right, there are several, each with unique characteristics designed for different needs. The EXT family, that's the extended file system, is probably the most common. It includes X2, X23, and X4.
Right, I've heard of those.
Yeah, XT4 is currently the most prevalent and generally the fastest. It offers journaling capabilities for data integrity, which is important. XT was notable as the first Linux file system capable of managing really large data volumes, up to 2 terabytes, which was significant back then.
Okay, what else?
Then there's JFS, the journal file system. It was developed by IBM, and it serves as an alternative to EXT. It's particularly beneficial in environments with maybe limited CPU processing power because its journaling is pretty efficient. RiserFS was an earlier default for a time. It was known for dynamically supporting file extensions and good performance with lots of small files. But due to some performance drawbacks and other issues, there was a general shift back towards X3 mostly.
Right.
XFS is a fascinating one. It's characterized as a high-speed, journaled file system explicitly engineered for parallel I/O processing.
Parallel I/O.
Yeah. An intriguing fact, which kind of demonstrates its capabilities in high-performance computing, is that XFS is actually used by NASA for managing vast data sets in supercomputing environments.
Wow, NASA.
Yeah.
That really highlights its robustness and speed. Okay, what else is there?
Then we have BTRFS, that's B-tree file system. It's designed with a focus on more advanced features like fault tolerance, self-healing capabilities, snapshots, efficient system repairs. It's a modern contender. And finally, the swap file system. It's distinct. It's specifically for memory paging within Linux operating systems. It's primarily used during system hibernation or when your physical RAM is exhausted. It acts as virtual memory on disk.
Okay.
For systems that never hibernate, swap space is often allocated to equal the amount of physical RAM just as a safety buffer.
Right. Now, when you look at a file listing in Linux using a command like lsll, it's not just a file name, right? There's a wealth of information, the file attributes, all those characters. How do we decode what we're looking at there?
Yeah, this is where you see the rich metadata that Linux meticulously stores about every file. The very first character in the LL output signifies the file's type.
Okay, the very first one.
The very first one. AD means it's a directory. A means it's a regular file. Pretty simple. But then you have C for character special file.
What's that?
That's used for sequential access to devices, like your terminal or a serial port. Essentially, a direct stream of data to or from hardware. And B signifies a block special file. That's typically for block-oriented devices like hard drives, CD-ROMs, SSDs, where data is accessed in fixed-size blocks.
Oh, okay.
These special files are how Linux interacts with your physical hardware at a very fundamental level. They're crucial for specific system configurations and direct device communication.
So that first character tells you exactly what kind of item you're interacting with. What about the next set of characters, those groups of RWX?
Right, those are the user permissions. And they are absolutely crucial for security and access control. R stands for read access, W for write access, and X for execute access.
Read, write, execute. Got it.
Each of these permissions also has a numerical value that administrators often use. Read is 4, write is 2, and execute is 1. These numerical values become critically important when you're changing permissions with commands like chmod.
Okay, 4, 2, 1. And these URAX permissions aren't just one set. They come in 3 distinct blocks, right? Can you break down what each block governs?
Exactly. The subsequent 9 characters are segmented into 3 distinct blocks of 3 permissions each, governing different access levels.
Okay.
The first block dictates user-owner permissions, defines precisely what the creator or owner of the file is allowed to do. The second block defines group permissions. This dictates the access rights for any users who belong to the file's assigned group. Incredibly useful for team projects.
Right.
The third and final block applies to other permissions. These apply to all other users on the system who are neither the owner nor part of the file's designated group. And a hyphen in any position just indicates the absence of that specific permission. So, for example, if you see RWX R-R-XR array, it means the owner has read, write, and execute. The group has read and execute, but no write. And all other users only have read access. This granular control is really a cornerstone of Linux security.
That's a lot of detailed information just from one line of output. That's like a secret language for system integrity. Okay. Now that we've laid the foundational concepts, it's time to equip ourselves with the Craftsman's Toolkit. We're moving into part 2, Essential Commands and Operations. If you're going to navigate the Linux landscape, the most fundamental command has to be else, right?
Yeah.
What's its primary function and how do administrators typically use it?
Indeed, else is arguably the most fundamental command for directory inspection. Its primary function is just to display the files and subdirectories within a given directory. It's your immediate window into what's inside any folder. For an administrator, though, else often comes with flags. When you add the all flag, as in LSLL, you get the long listing format. That reveals all those detailed file attributes we just discussed: permissions, number of links, owner, group, size, timestamps, all that stuff.
All that stuff. It's like going from a quick glance to a detailed inventory. And remember, a great general rule for any command is you can usually type command help or command demand for manual page to discover all its various options and flags.
A great tip for anyone getting started. Okay, what about moving between those directories once we've listed them? CD is the command for changing directories.
Yeah.
How do we traverse the file system efficiently?
CD is how you move through the directory tree. It's your primary navigation tool. To move up one directory level, you use CD ...
Okay.
To jump directly to the root directory from anywhere, it's CDD. And CD tilde is a handy shortcut to bring you back to your user's home directory.
Yeah. A crucial, often overlooked tip for newcomers. If a directory name contains spaces like my documents, you must enclose the entire name in quotation marks, like CD my documents.
Ah, the quotes.
Yes. Otherwise, the shell interprets the spaces as separate arguments and you get errors. This simple rule saves a lot of frustration.
Got it. And what about creating new directories to keep things organized?
For that, you use MP. It's straightforward. mkdir my new folder. A particularly useful flag for administrators is mkdir party
-P.
-p. This allows you to create intermediate parent directories if they don't already exist. Or you can create multiple nested subdirectories in a single command, like mkdir project subfolder data. Saves a lot of manual steps when setting up complex directory structures.
And then to clean up, armdir for removing directories. Is there anything special to know about that? Maybe a common pitfall?
Yes, armdir is specifically used to remove empty directories. This is its key limitation and often a source of frustration for new users. If there are any files or subdirectories inside, armdir will fail.
Okay, only empty ones.
Only empty ones, like MADDHE, RMDP, and EP, can remove a child directory and its parent if the parent becomes empty after the child removal. Adding V for MADIGDHB gives you verbose output, showing you exactly what's being removed. Useful for debugging or just confirmation.
Right.
If you need to remove non-empty directories, you typically use rmdchar, but that's a much more powerful and potentially dangerous command we'll probably get to.
Okay, good to know. Perfect for keeping things tidy.
Yeah.
Now let's move to sculpting information. Basic file operations. First, creating new empty files with touch.
Touch is the quick and easy way to create new empty files in the current directory. For example, touch new report.txt. It's also frequently used just to update the timestamp, the last modified date time of an existing file without actually modifying its contents.
Oh, interesting. Why would you do that?
That can be useful for triggering certain scripts or build processes that look at file modification times.
Ah, okay. Then CP for copying files or directories. What are the key flags administrators commonly use to manage copying more effectively?
The CP is used to duplicate files or directories. The basic syntax is CP source destination. Important flags that administrators rely on include SI for interactive mode.
Interactive.
Yeah, which prompts you for confirmation before overwriting an existing destination file, a great safety net.
Definitely.
ADA for update, which copies only if the source file is newer than the destination or if the destination file doesn't exist. Useful for synchronizing directories. And SV for verbose, showing you the progress and exactly what files are being copied. Invaluable for large operations.
Mm-hmm.
You can also use wildcard characters like .txt to copy multiple files of a specific format at once. Massive efficiency boost.
So you can officially copy all text files, for example, or only those that have changed. What about MV for moving or renaming? Is it similar to phi in its functionality or flags?
MV is essentially the cut-paste equivalent in Linux. It relocates the source file or directory from its original location to a new one, meaning the original is gone.
Right, cut paste, not copy paste.
Exactly. It's also the primary command you use to rename files or directories. For instance, mv oldname.txt newname.txt. And yes, it shares similar useful flags like IInteractive, AU update, and V verbose with CP, offering those same levels of control and feedback.
Okay. And for deletion, there's R. Anything to be aware of?
Yep.
Perhaps a common cautionary tale.
ARM is the command to delete files.
Yeah.
And this is where a significant caution comes in. Unlike some graphical interfaces, files deleted with ARM are typically not moved to a recycle bin.
All right, no recyclable.
No recycle bin. They are gone immediately and often unrecoverable without specialized tools or backups. So RM should always be used with precision and care, especially when combined with powerful flags like R-recursive for directories or force. A common anecdote or nightmare really is the RM-RF disaster, which can wipe out an entire system if executed by an inexperienced or careless root user. Use with caution.
A powerful command, indeed, demanding respect. Okay, now let's get into decoding and manipulating data. Text processing and redirection. CAT is a classic. How do administrators primarily leverage it?
CAT, short for concatenate, is a versatile command, primarily used to display the entire content of text files directly to your terminal. So catmylog.txt would just dump the whole log.
Right.
It's also powerful for joining the content of multiple files into one seamless output, hence concatenate. Crucially, cat combined with the redirection symbol can be used to create new text files, like catnewfile.txt. Then you type your content and press Ctrl plus D.
Ah, okay.
Or you can use double greater than to append new text to existing ones. Makes it a very handy tool for quick file manipulation right from the command line.
That's a versatile one. And then grep, the powerful search tool. How does it become indispensable for administrators sifting through logs or configuration files?
Oh, grep. It stands for a Global Regular Expression Print, and it's an incredibly powerful text search tool. Indispensable for finding specific strings or patterns within text files, which could be massive log files or complex configurations. The basic usage is grep search string file name, but its versatility truly shines with flags, -I for case-insensitive search, -N to display matching lines with their line numbers, invaluable for troubleshooting code or configs.
Yeah, the line numbers help a lot.
Definitely. -E to display lines not matching the search string, which helps filter out noise. And -E to simply count the number of lines where the string was found, giving you a quick summary. Imagine searching through gigabytes of logs for a single error code. grep does it in seconds.
So you can quickly find patterns or specific information in large files. What about sort? When do you typically reach for that command?
Sort is used to order the lines of text files or the output of other commands, either alphabetically or numerically. It's perfect for making sense of unstructured data. Basic usage is sort file name. Key flags include R for reverse order, descending, -F for case-insensitive sorting, and -N for numerical sorting, which is important for lines starting with numbers so they get sorted correctly as numbers rather than just as strings. Crucial when analyzing data like user IDs or process counts.
And then there's the famous pipe command. This is a fundamental Linux concept that allows for incredible efficiency, isn't it?
It is, and it's where the real power of the Linux command line truly emerges, I think. The pipe takes the standard output of one command and feeds it directly as the standard input to another command.
Output becomes input.
Exactly. It's fundamental because it allows you to chain commands together, creating complex and highly efficient workflows without needing to create intermediate files. A classic example might be cat varlog syslog grep error sort R.
Okay, break that down.
So this command first displays the syslog, cat, then filters it for lines containing error, grep, and finally sorts those error lines in reverse alphabetical order, sort error, all in one fluid operation. Saves immense amounts of time and manual effort. It really shows the power of composability.
That's where the magic starts to happen. You're essentially building custom tools on the fly. Okay, now let's talk about guarding the gates, permissions, and ownership. Why are these concepts so crucial for security in Linux?
Permissions are absolutely critical for securing files and directories in Linux. They are a primary security mechanism. They restrict who can read, write, or execute content, which is fundamental for maintaining system integrity and data confidentiality. Without proper permissions, sensitive configuration files, user data, even system binaries could be tampered with or accessed by unauthorized users. That could lead to system compromise or data breaches. Understanding and managing them is just non-negotiable for any administrator.
And chmod is the command to change them. What are the two main practical ways administrators use chom to modify permissions?
There are two primary modes for chmod. The first is symbolic mode. This is often more intuitive for granular changes. It uses characters, .u for use owner, G for group, O for others, or A for all, combined with operators, plus to add permission, to remove permission, or to overwrite and set exact permissions.
Okay, like G plus W.
Exactly. Like chmod G plus W file adds write permission for the group, or chmod OX file removes execute permission for others. This is great for incremental adjustments.
Right. And the other mode?
The second is octal notation, also called absolute mode. This is favored for quickly setting precise, complete permission sets. This uses the numerical representation we discussed earlier. Read 4, write 2, execute 1.
4, 2, 1 again.
Yep. You sum these values for the user, group, and others to create a 3-digit octal number. For example, 755 translates to RWX for the owner, 4 plus 2 plus 1, RDEX for the group, 4 plus 0 plus 1, and RX for others, 4 plus 0 plus 1.
Okay, 755 is common.
Very common. A powerful illustrative example is chmod 700 important script.esh that grants full read, write, and execute permissions only to the owner, effectively denying any access to the group or others. This is common for personal scripts or sensitive files.
So you can be incredibly precise about who can do what with a file, vital for security. And beyond permissions, there's also the concept of ownership. How do you change who owns a file or which group it belongs to?
For changing the owner of files and directories, you use chown. For example, chown user mydocument.txt changes the owner to nuser. And to change the group ownership, it's cheat-hdrp. For instance, cheat-hdrp admin team my project would assign the admin team group to that directory.
Okay, chown and cheat-hdrp.
These commands are essential for proper access control, ensuring the right users and groups have the appropriate privileges, especially in multi-user or team environments.
Shifting gears a bit, let's talk about the system's pulse. Some key utilities for monitoring and control that are part of every administrator's daily routine. First, PS.
Right, PAS. It's the command to query the process table and see what processes are currently running on your system. It gives you a snapshot of active programs and their PIDs. PIDs, it's often combined with flags like O for more detail, like PO to see processes owned by all users, or TSESEF for a full listing with parent-child relationships, which is critical for troubleshooting misbehaving applications.
Okay. And there's a whole set of commands for job control, like Control plus C or Control plus Z, BGFG jobs. What do these do, and how do they allow administrators to manage live processes?
Yes. These are essential for managing running programs directly from your terminal session. Control plus C immediately stops a currently running foreground process. Think of it as a quick kill button for what you're currently interacting with.
Okay.
Control plus Z is different. It suspends a running foreground process, moving it to a paused or stopped state without terminating it.
Suspends, not kills.
Right. Once suspended, you can use B background to send that process to run in the background, freeing up your terminal for other tasks. FG foreground brings a background job back to the foreground so you can interact with it again. And jobs displays a list of all current jobs processes associated with your shell, showing their status, running, stopped, etc.
So you can juggle tasks.
Exactly. This allows an administrator to manage multiple tasks concurrently from a single terminal. It's a huge productivity boost.
So you can pause, restart, or background tasks for efficiency. And if you need to completely stop a process that's misbehaving or stuck.
That's where kill comes in. It's used to terminate a process by supplying its process ID, PID, or job ID. You might use kill 12345, where 12345 is the PID you found using PPES. There are also different signals you can send with kill. For example, kill night is 9 is a forceful, non-recoverable termination, often called the kill hammer or just killing a process, used when a process won't respond to a normal kill.
Okay, the hammer. And for tasks that need to run regularly without human intervention, cron tab comes into play.
Yes, contab.
Yeah.
It's the command used to interact with the cron service, which is a time-based job scheduling daemon. Cron starts when the system boots and runs indefinitely, executing commands or scripts at specific dates and times defined in the cron tab file. It's incredibly powerful for automating routine system maintenance tasks like rotating log files daily, running nightly backups, or updating databases at specific intervals. It ensures critical tasks happen reliably even when no one is logged in.
For recalling past commands, which is incredibly useful when you're doing repetitive tasks or debugging, history is invaluable, right?
Oh, absolutely. History allows users to view previously executed commands. This isn't just for remembering, it's a huge time saver. You can rerun commands or modify them easily.
Okay.
You can even use History 5 to see just the last 5 commands you ran. Or use bang to rerun command number N from the history list, or bang to rerun the very last command. It's an administrator's best friend for efficiency and debugging.
Very handy. How about checking memory usage, a critical metric for system performance?
For that, you use free. It displays the total amount of free and used memory, including physical RAM and swap space. It's a quick way to gauge if your system is running low on memory, which can significantly impact performance. A useful flag is free H for human-readable output. Makes it much easier to interpret megabytes or gigabytes instead of just raw bytes.
Good tip. And for network status, ifconfig or ip address are the go-tos.
Yes. Ifconfig is a classic command, though technically deprecated now in favor of ip address, which is part of the epr2 suite.
Ip address is the newer one.
It is. Both are used to show the current IP address and other network interface configurations like MC addresses, network masks, broadcast addresses, network traffic statistics. You'll still find ifconfig widely installed on many systems, but ip address offers more granular control and is the modern standard, especially for scripting.
Finally, hostname. Simple enough.
Pretty simple. Hostname just displays the hostname of the system, identifying your specific machine on the network. If you want the fully qualified domain name, FQDN, which includes the domain part like myserver.mydomain.com, you can usually use hostname-f. This is important for services that rely on a unique, resolvable name.
Okay, we've covered the foundational concepts and built a solid toolkit of commands. Now, in part 3, we're going to talk about orchestrating the system specifically, process and user management. This is where you really take control of the operating system's activity. Let's start with the life of a process. What defines a process in Linux, and why is understanding its life cycle so vital for an administrator?
Right. So a process is simply an instance of a running program. When you launch an application, run a command, or even when the system boots up, various programs get executed, and each one becomes a process running on the system.
Yep.
Understanding their life cycle, how they start, how they consume resources like CPU and memory, how they communicate, how they terminate is absolutely vital. Administrators need to identify rogue processes that might be consuming too many resources, understand parent-child process relationships, and ensure critical services are always running. It's fundamentally about keeping the system healthy and responsive.
And we touched on this briefly, but can you elaborate a bit more on foreground versus background processes and why managing them effectively is so important for administrators juggling multiple tasks?
Certainly. Foreground processes are the ones that interact directly with you, the user, and they occupy the terminal session. You see their output, and they typically wait for your input, like running a script that continuously prints status updates.
Right in front of you.
Exactly. Background processes, however, run independently. They don't tie up the terminal, allowing you to continue working on other tasks or even log out while they complete their job. The commands we discussed earlier, Control+C to stop, Control+Z to suspend, bbrand to move to background, FJ to bring back to foreground, and jobs to list active processes. These are crucial for managing this. They let administrators efficiently control the execution state of processes, manage resource allocation, and ensure system responsiveness. This is vital for maintaining a productive and stable system, allowing one administrator to manage multiple complex operations simultaneously.
That makes perfect sense for efficiency, letting you multitask effectively. Okay, now, let's talk about who's who. User administration. What are the different types of users in a Linux system, and why are these distinctions important for security and management?
Yeah, Linux systems typically distinguish between 3 crucial types of users, each with distinct privileges and roles. First, you have regular users.
Okay.
These are the accounts created for typical daily use by individuals. Their personal files and folders are usually stored within their dedicated home directories, like home username. They generally have limited access to other users' directories, which ensures privacy and prevents accidental or malicious interference, a key security feature.
Right, standard user account.
Exactly. Second, the administrative root user. This is the super user account, automatically created during Linux installation. The root user possesses ultimate, absolute control over the entire system.
God mode.
Pretty much. They can access any file, install system-wide software, modify any configuration, perform any administrative task without permission limitations. It's critical to emphasize the immense power of this account. Using it injudiciously can lead to catastrophic system damage. Administrators are taught to use this account only when absolutely necessary and with extreme caution.
Okay. And the third type?
Finally, service users. These are special accounts created for specific system services or applications, like an Apache web server, a SCRID proxy, or an email service. These accounts are designed with restricted privileges.
Like that.
Well, for example, a web server might only need read access to web files and write access to a specific log directory. It doesn't need full root access. This isolation enhances system security by limiting the potential damage if a specific service gets compromised. They just run in the background, performing their dedicated functions with minimal necessary rights.
So different levels of privilege for different needs. A core tenet of security. And how do regular users gain elevated privileges to perform administrative tasks without constantly logging in directly as the highly powerful and therefore risky root user?
That's where suit, substitute user, and especially sudo, super user do, come in. Sudo is particularly important, and it's really a cornerstone of modern Linux security.
Sudo. Hear that one a lot.
You do. It allows a permitted regular user to execute a specific command as the super user root, or even another user, without needing to log in directly as root.
Okay.
This method is far safer because it limits the time spent operating with full root privileges, reducing the risk of accidental damage or malicious activity. When you use sudo, you're only granting elevated privileges for that specific command, and it often requires your own password, leaving an audit trail. It's like getting a temporary supervised pass to the command center rather than just living there.
Very smart for security and accountability. And beyond individual users, there's the critical concept of groups. How do administrators leverage groups for more efficient management?
Yes. Administrators can, of course, add and remove individual user accounts. But, crucially, they organize users into groups. A group can contain multiple users, which greatly simplifies the management of file and directory permissions.
How so?
Well, instead of setting permissions for each individual user on a shared directory or file, you can apply permissions to an entire group. For example, all members of the dev team group could be given read and write access to a shared project directory. It dramatically streamlines access control and makes it much easier to add or remove team members later.
Essential for managing larger teams or complex project structures. Okay, now, for the system's health check, monitoring, we mentioned free from memory. Why is monitoring memory and disk usage such a critical ongoing task for system administrators?
Monitoring memory and disk usage, often with tools like free from memory and DF, disk-free, or disk usage for storage, is a critical ongoing task because it's directly tied to system performance and stability. A system running low on RAM will start swapping heavily to disk, which dramatically slows everything down. A full disk, especially if it's the root partition or log directories, can bring an entire system to a grinding halt. It can prevent new processes from starting or critical services from writing data.
Right, that sounds bad.
It is bad.
Right.
Proactive monitoring helps administrators prevent storage-related issues, identify performance bottlenecks, and ensure overall system health before problems escalate into outages.
And for more advanced flexible disk management, there's something called Logical Volume Manager, or LVM. What's its key advantage compared to traditional rigid disk partitioning?
LVM. It's an advanced and incredibly powerful partitioning tool that offers unparalleled flexibility in storage management. Its key advantage, the real game changer, is the ability to resize or shrink logical volumes after they have been created.
After create.
Yes. This is huge compared to traditional fixed disk partitions, where size adjustments are often complex, disruptive, or even require data loss and reformatting. With LVM, an administrator can dynamically expand a file system to accommodate growing data needs, often without downtime, or even shrink it if space is reclaimed.
Wow.
This is a significant benefit for dynamic storage management in server environments. It allows resources to be allocated and reallocated on the fly, avoiding the painful repartitioning process that plagued older systems. It fundamentally transforms how you think about disk space allocation.
That's a huge plus for scalability and adaptability.
Yeah.
Okay, and finally, why is system logging so profoundly important for administrators? And how does CRON tab help manage it?
Monitoring and managing system log information is absolutely vital. Logs are essentially the system's diary, its memory. They are indispensable for troubleshooting problems. I mean, every error, every security event, every service start or stop is often recorded somewhere in the logs. They are critical for performing security auditing to detect unauthorized access attempts or suspicious activity, and for understanding system behavior and performance trends. Without logs, diagnosing issues would be like trying to solve a mystery without any clues.
Right.
CRON tab is crucial here because logs can grow very large very quickly. Administrators often use cron jobs to automate tasks like log rotation. This archives old logs and starts new ones periodically, preventing disks from filling up and ensuring logs remain manageable and available for analysis when needed.
As our deep dive continues, we're now entering Part 4, the digital highway networking and services. In today's interconnected world, understanding network basics is, well, fundamental. Let's start with the absolute foundation, IP addressing. What are IP addresses and why are they so crucial for communication?
Right. IP addresses are the foundational numerical labels assigned to every single device that wants to communicate across a network, whether that's your laptop, a server, your phone, maybe even a smart toaster these days.
Yeah, everything has one.
Pretty much. They act as unique identifiers, much like a street address for a house. Without an IP address, devices simply couldn't find each other, couldn't send data, or receive information. They are the bedrock of all modern network communication.
And we often hear about IPv4 with its characteristics and classes. Can you explain that structure and how it relates to subnet masks?
Sure. IPv4 addresses are 32-bit numbers, most commonly represented in 4 sets of numbers separated by dots, like 192.168.1100. Historically, they were divided into IP classes, Class A, B, and C, which determined the default network size and how many hosts it could support. A subnet mask, like 255.255.255.0 for a typical home network, then divides an IP address into 2 logical parts. The network ID, which identifies the specific network segment the device belongs to, and a host address, which identifies the specific device within that network.
Part and host part.
Exactly. So if your IP is 192.168.1100 and your subnet mask is 255.255.255.0, then 192.168.1 is your network ID and 100 is your host address on that network. Modern networks largely use CIDR classless interdomain routing, which is a more flexible and efficient way to subdivide networks, moving beyond those rigid classes.
Right.
It's also important to know about private IP ranges, things like 10.0.0.08, 172.16.0.168.0.016. These are non-routable addresses used for internal networks. They're not accessible from the public internet. This helps conserve public IP addresses and provides an extra layer of security.
So internal networks use these private IPs separate from what's directly on the internet. Okay, and what about IPv6? We hear about it often, but what are its core advantages over IPv4?
IPv6. It's the next generation of IP addressing, yeah. It was primarily developed to address the critical exhaustion of IPv4 addresses as the internet just grew exponentially.
Ran out of numbers.
Pretty much. Its most obvious advantage is its vastly larger address space. It uses 128-bit addresses, meaning there are virtually an infinite number of unique addresses available. Solves the scarcity problem.
Okay.
But beyond just numbers, IPv6 incorporates built-in IPsec for enhanced security at the network layer. It vastly improves efficiency for mobile devices and peer-to-peer applications by simplifying routing. And it allows for stateless auto-configuration, making device setup much simpler. It's really designed for the future of the interconnected world, enabling the Internet of Things and more. Understanding its basic strengths is key for advanced network understanding.
Clearly an important evolution, especially as everything becomes connected. And then there's the concept of hosts and host names. How do these help us navigate the network more easily?
A host is simply any device connected to a network that has an IP address. Could be a server, a router, your phone, anything. A host name is a human-readable, memorable name like google.com or my web server or database01 that corresponds to a numerical IP address. It just makes it infinitely easier for us humans to remember and access network resources than having to memorize long strings of numbers.
Yeah.
It's the user-friendly alias for a complex numerical identifier.
Makes total sense. Okay, now let's arm ourselves with the networker's arsenal. Essential network tools that administrators use daily for diagnostics and configuration.
Yeah.
First, ping.
Ping. Basic but absolutely essential diagnostic tool. It's used to check network connectivity and determine if a host is reachable on an IP network.
How does it work?
It sends small packets called ICMP echo requests to a target and measures the round-trip time for a response. It tells you if a connection exists, how quickly it responds latency, and if there's packet loss. It's often the very first command an administrator runs when troubleshooting network issues. Can I even reach that server?
And if config or address, again, for network interfaces.
Yes. These are your go-to commands for displaying and configuring network interface parameters. That includes the system's current IP address, subnet mask, broadcast address, and the MSE address, the hardware address. While ifconfig is a classic and still very common, EAP address, part of the EAP-root 2 suite, is its modern replacement. It offers more granular control and is becoming the preferred tool for scripting network configurations in newer Linux distributions.
For securely managing remote Linux servers, SSH is a crucial tool. How has it revolutionized remote administration?
Oh, absolutely. SSH, or Secure Shell, is a cornerstone tool for secure remote access and management of Linux servers. Its native support in Linux revolutionized remote administration. It allows administrators to execute commands, transfer files securely, and establish encrypted communication channels over an unsecured network, like the internet.
Encrypted is key.
Absolutely. Before SSH, remote connections were often in plain text, making them vulnerable to eavesdropping. SSH provides strong encryption and robust authentication mechanisms, like public-private key pairs, protecting sensitive administrative sessions from eavesdropping and unauthorized access. It means you can manage servers across the globe as securely as if you were sitting right in front of them.
And what about firewall basics, like IPTables? Why are firewalls so critical for network security?
Firewalls are critical for implementing basic network security by controlling incoming and outgoing network traffic at a granular level. IPTables is a common command line utility used to set up, maintain, and inspect the IP packet filter rules in the Linux kernel.
Like a gatekeeper.
Exactly like a gatekeeper. It inspects every packet trying to enter or leave your system and decides whether to allow it based on predefined rules. It blocks unwanted connections and permits legitimate ones. You define rules based on source to destination IPs, ports, protocols. While firewalls can introduce complexities like needing specific rules to allow SSH access or maybe requiring RSA keys for authentication, they provide vital protection against unauthorized network access and common attack vectors. Administrators spend considerable time configuring these rules to create a secure perimeter.
So it's about balancing necessary access with robust security. Okay, now let's talk about some core services that underpin the entire internet, starting with DNS, the domain name system. It's often called the internet's phone book, right?
Precisely. DNS is the primary distributed naming system that translates human-readable domain names, like google.com, into numerical IP addresses, which are what computers actually use to identify each other on the network. It also performs the reverse translating an IP address back to a host name, known as a reverse lookup. Without DNS, you'd have to type, 142.250.187.164 into your browser to reach Google. Clearly impractical. It's the silent global directory service that makes the internet usable for humans.
And how does that translation process, what's called DNS resolution, actually work step by step? It sounds complicated given the scale of the internet.
It is an intricate hierarchical dance, but it happens incredibly fast, usually in milliseconds. When you type a domain name into your browser, say example.com, a resolver software, usually on your computer or your ISP's network, initiates the query.
Okay, the resolver.
Right. 1. If the IP isn't in its local cache, the resolver first queries the root servers. These are the very top of the DNS hierarchy.
The roots.
Yep. 2. The root servers don't know the exact IP, but they know who manages the top-level domains. So they direct the query to the appropriate top-level domain, TLD servers like those for .com, .org, or .net. 3. The TLD servers then point to the authoritative name servers for that specific domain, Ubiquity, for example, .com. These are the servers that actually hold the record mapping the domain name to its IP address.
The ones with the real answer.
Exactly. 4. The resolver then receives this IP address and typically caches it locally for faster future lookups before finally sending the response back to your system. Then your browser can connect to the correct web server. This whole process is distributed globally, making it incredibly resilient.
That's quite a journey for a simple website address, happening completely invisibly to us. Now, our sources provide a detailed overview of configuring a DNS server using Bind, which I understand is one of the most popular DNS servers. For those aspiring system administrators, this is where the theoretical meets the practical. Can you walk us through the conceptual phases and key considerations involved rather than just a step-by-step manual?
Absolutely. Setting up a DNS server like Bind, Berkeley Internet Name Domain, is a foundational skill. And yeah, thinking about it in conceptual phases is probably more useful than just reciting steps.
Okay.
Phase 1. Installation and basic network setup. First, obviously, you install the Bind software package using your distribution's package manager, yum, apt-get, whatever. Crucially, the DNS server must have a static IP address.
Static, not dynamic.
Right. If its IP changes, clients won't be able to find it consistently. So you configure your network interface to use a fixed IP, not DHCP. You also assign your DNS server a fully qualified domain name, FQDN, like dns1.yourdomain.com, and add this to your local echosts file for internal resolution, giving it a permanent home and a name.
So you're giving it a permanent home and a name it recognizes locally. What's the next big phase?
Phase 2, initial configuration of Bind. The core configuration happens in a file usually called named.conf. Here, you'll specify that bind should listen for queries on your server's static IP address, not just localhost. You'll typically disable IPv6 listening if you're not using it, just for simplicity. Most importantly, you define who is allowed to query your server using the allow query directive. Typically any for a public DNS server or maybe specific internal networks for a private one.
Right, who can ask questions?
Exactly. A common pitfall here is forgetting to allow queries from the client machines, which leaves them unable to resolve names through your new server.
That makes sense, telling the server where to listen and who to respond to. After that, you start defining the zones. What are those?
Phase 3, defining DNS zones. This is where you tell bind what domains it's authoritative for, meaning which domains it holds the official records for. You'll define forward lookup zones, which translate domain names, like example.com, into IP addresses. And you'll define reverse lookup zones, which perform the inverse, translating IP addresses back into domain names.
Forward and reverse.
Correct. For reverse zones, there's that common trick. The subnet is specified in reverse order, like 2.56.168.192.in-adder.arpa for the 192.168.56.x network. This structure allows the DNS system to efficiently manage both lookups across its distributed hierarchy. This configuration file essentially tells bind, if someone asks for this domain, go look in the specific file for the answer.
Okay, so you define the areas of responsibility for your DNS server.
Mm-hmm.
And then you need the actual data, the actual records for those zones, right?
Yeah. Phase 4. Creating zone files. Exactly. In a specific directory, usually var named, you create the actual zone files. For example, forward.zone and reverse.zone. These files contain the specific DNS records.
Like the phone book entries.
Precisely. Like A records, address records, that map host names to IPv4 addresses, AAA records for IPv6, PTR records for reverse lookups, MX records for mail servers, NS records for name servers. These are the actual entries. A small but important administrative detail here is ensuring correct file permissions and group ownership for these zone files, often setting them to be owned by root or the named group for security reasons.
So you're populating the phone book with entries.
Yeah.
And the final step to make it all live.
Phase 5, activating the service. After all configurations are complete and the zone files are populated, you must restart the bind service. Typically with system actual restart named or service named restart, this forces bind to reread its configuration and zone files. Only then will your DNS server begin resolving names for clients. And crucially, for clients to actually use your new DNS server, you also need to update their etcresolve.conf file to point to your server's static IP address. It's a comprehensive process, but once you understand the concepts, it's quite logical.
Wow, that's a comprehensive process, truly showing the depth of what system administrators do to make the internet work. Are there alternatives to bind, though, or is it universally dominant?
While bind is very popular and, widely used, especially historically, other robust DNS server software options definitely exist. For example, Unbound is known for being a validating, recursive, and caching DNS server. It's designed for high performance and security, often used just for local DNS resolution.
Okay.
Another one is Power DNS. It's highly versatile and supports various backends, including databases, which makes it suitable for complex dynamic environments. So while bind is foundational, administrators do have choices based on specific needs.
Beyond DNS, what are some other key network services in Linux that administrators commonly manage?
Oh, another crucial one is DHCP Dynamic Host Configuration Protocol. This protocol automatically assigns dynamic IP addresses and other network configuration parameters like DNS server addresses and default gateway information to devices connected to a network. It really simplifies network setup for clients.
Like when you connect to Wi-Fi.
Exactly. Imagine connecting a new phone to Wi-Fi. DHCP is what gives it an IP address automatically so it can get online. Then there are other vital services like FTP servers, file transfer protocol, for efficiently transferring files, though less common now maybe than things like SCP or SFTP. And proxy servers, which act as intermediaries for client requests. They're often used for security, caching web content to speed up browsing, or enforcing access control within a network. These services are really the backbone of many network operations.
We've covered a strong foundation in concepts, built a solid toolkit of commands, and understood how to orchestrate core processes and users. Now, as we approach the end of our deep dive, let's touch upon Part 5. Beyond the basics, advanced topics, and exam focus. First, file links. We heard earlier that Linux supports both hard and soft links. What's the key practical difference an administrator needs to be aware of? And what are their respective use cases and pitfalls?
Right. File links. Linux indeed offers two distinct types, hard links and soft links, also known as symbolic links or symlinks. Understanding their differences is crucial because they behave very differently when original files are moved or deleted. This can have significant implications for data integrity and system behavior.
Okay, so how does a hard link work?
A hard link is essentially just another name pointing to the exact same file data on the disk. The file data itself has a reference count. Creating a hard link just adds another name pointing to that data and increments the count.
Like two keys to the same box.
Exactly like having two keys to the exact same safe deposit box. If you delete one of the keys, one file name, the box and its contents, the actual data, are still perfectly accessible with the other key, the other hard link. The data is only truly deleted when the reference count drops to 0. All hard links to a file share the same inode number. They have limitations, though. They can only exist on the same file system and generally cannot link to directories. They're great for maintaining multiple paths to the same data, ensuring data persistence even if a primary path is removed, or for simple versioning where you want snapshots without duplicating data.
Okay. And soft links.
A soft link, conversely, is just a pointer to the path of the original file. Much like a shortcut in Windows or an alias in macOS, it contains the text string of the path to the original file.
Like a sticky note with directions.
Perfect analogy, a sticky note with directions to a building. If the original file, the building, is deleted or moved, your sticky note, the soft link, becomes useless. It points to nothing. It's a broken link. Soft links, however, can link across different file systems and can link to directories, which is a major advantage. This makes them critical for creating convenient shortcuts, establishing flexible paths for applications that expect files in specific locations, or building complex directory structures without physically moving data around.
And a pitfall.
The common pitfall for new administrators is accidentally deleting the original file that a soft link points to. This leads to a non-functional shortcut, which can be confusing to debug if you don't realize you're dealing with a link and not the actual file.
That distinction is incredibly important to avoid accidental data loss or frustrating broken links.
Wow.
Okay, next, safeguarding data. Backup and restore procedures. Why are these so absolutely vital for any system administrator?
Robust backup and restore procedures are not just important, they are absolutely vital, foundational. They form the cornerstone of data integrity, business continuity, and disaster recovery planning. In the real world, hardware fails, software gets corrupted, humans make errors. It happens. A reliable backup strategy ensures that data can be recovered quickly and completely in case of accidental deletion, corruption, system failure, or even malicious attacks like ransomware.
Right, ransomware is a big one now.
Huge. Without backups, an organization risks catastrophic data loss, potentially prolonged downtime, and severe financial and reputational damage. It's the ultimate insurance policy for your digital assets. Non-negotiable.
And how do shell scripts play a role in automating these critical backup processes across a network?
Shell scripting is incredibly powerful for automating network backups. It transforms what could be a manual, tedious, error-prone task into a reliable, scheduled operation. Administrators can craft scripts that perform a sequence of actions. First, they might mount shared network directories, maybe using SIPs for Windows shares, Common Internet File System, or NFS, Network File System, for Linux Unix shares to gain access to remote storage.
Okay, connect to the storage.
Then, they use commands like cpe-degu to copy only updated files, or maybe rsync, which is a very powerful tool specifically designed for efficient incremental backups, or tar for archiving and compressing entire directories. They copy critical files and directories to these mounted network locations.
Okay.
These scripts can incorporate error checking, logging, and crucially, be scheduled with cron tab to run automatically overnight or during other low traffic times. They reflect changes between local systems and the shared backup storage. This really shows how all those individual commands we discussed earlier combine into immensely powerful administrative tools for real-world scenarios.
That's a truly practical application of all those commands.
Yeah.
Forming a powerful automated solution. Okay, now let's talk about Fortress Linux. Security considerations. We've mentioned iptables before, but why is it so fundamental for controlling network traffic?
Yes, iptables is fundamental. It's the Linux utility for configuring the kernel's packet filtering rules, essentially acting as the system's built-in firewall. It's fundamental because it allows administrators to control network traffic at a very low level. You can define granular rules for incoming and outgoing connections based on source-to-destination IP, port numbers, protocols, connection states, and more. This control is paramount for network security. It allows you to block unwanted access attempts, restrict services to only necessary ports, and protect your system from various network-based attacks. Without a properly configured firewall, your system is basically an open target on the internet.
And you mentioned earlier that Linux is inherently more secure than many other operating systems. Can you elaborate on why that's the case beyond just IPSables?
Yeah, Linux is renowned for being inherently more secure, and it goes beyond just having a firewall. This robust security stems from several architectural and philosophical design choices. Firstly, its permission model is very strict, requiring explicit permissions for almost everything, as we discussed.
Right, the RX.
Exactly. Secondly, it strongly adheres to the principle of least privilege. This means users and services are typically granted only the minimum necessary permissions to perform their functions, limiting potential damage if compromised. Third, its open source nature means its code is continuously scrutinized by a global community of experts. They quickly identify and patch vulnerabilities, leading to very rapid response times for security issues compared to closed source systems sometimes. The fact that traditional antiviruses are often not considered strictly necessary on many Linux systems is a testament to this strong, community-driven security posture. It's a system built from the ground up with security in mind, and it's constantly being reviewed.
And SSH isn't just a remote access tool, but also a crucial security feature, correct?
Absolutely. SSH is a critical security feature for managing remote Linux servers. Its native integration provides encrypted communication for all administrative sessions, protecting credentials and data from eavesdropping and unauthorized access over potentially insecure networks. Beyond basic password authentication, SSH strongly supports public key authentication, which is far more secure. It allows administrators to log in without sending passwords over the network at all. It's really the secure backbone for remote administration, ensuring that sensitive management tasks are protected end to end.
Finally, let's talk about some key system files that administrators interact with regularly. One mentioned in our sources is etc. password. What's its significance and what kind of information does it contain?
Etc. password, yeah. It's a particularly important system file. It acts as a database for all user accounts on the system. It contains essential user account information stored in a clear colon-separated format.
Colon-separated, okay.
Yep. For each user, you'll typically find their username, then a placeholder, usually an X, for the password. Historically, the encrypted password was stored here, but for security, it now points to the etc. shadow file. Then you have their user ID, UID, their primary group ID, GID, a comment field, often used for their full name, their home directory path, and finally, their default shell, which is the command line interpreter they use upon login, like bin bash. While the actual hashed passwords are now securely stored in etc. shadow and are only accessible by root, etc. pass remains fundamental for user administration. It allows the system to identify and authenticate users, and it lets administrators quickly see a summary of all existing accounts on the system.
Well, we've covered a tremendous amount of ground in this deep dive. I mean, from the fundamental role of Linux system administrators and the unique, powerful features of the Linux OS.
Yeah, the architecture.
Its underlying architecture, the essential commands that form the daily toolkit, and core concepts in process management, user administration, networking, foundational security. Wow, you've just absorbed a wealth of information that truly underpins the digital world.
We truly hope this deep dive has provided you with a clear, concise, and thorough understanding of these complex topics. This knowledge, it's not just a collection of facts, right? It's really your starting point into a vast and incredibly rewarding field.
And remember, this is just the beginning. The world of Linux is immense. It offers endless opportunities for learning and innovation.
Yeah.
We strongly encourage you listening to actively engage with this material.
Get your hands dirty.
Exactly. Experiment with the commands we discussed. Perhaps even set up your own Linux virtual machine or container for hands-on practice. True mastery and the deepest insights really come from getting your hands dirty in the terminal.
So as you move forward, maybe consider this. In a world increasingly shaped by complex, often opaque digital systems, understanding the transparent and powerful mechanics of Linux doesn't just equip you with technical skills.
Right.
It grants you a unique, empowering lens to critically analyze, actively control, and profoundly innovate the digital landscape that surrounds you.
What will you choose to build, secure, or simplify with this deepened understanding? We can't wait to see. Thank you for joining us on the Deep Dive.